السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله now we will switch gears to talk about Storm. Okay. So the roadmap for Storm, we will cover the data model, we cover system architecture, and we also will also cover one of the examples, kind of a complete example, and then we'll have a quick comparison between Storm and SparkStream. Okay, let's start with Storm. So before Storm, Storm is not new, by the way. We'll see a quick history of it. It was around 2012 or 13 when we had Storm for the first time. Before that, it was really hard to manually build a real-time system. Okay? Doing it with network of queues and workers and synchronizing between them, that was really, really hard. And it has lots of serious limitations. But Storm, the idea or the goal of Storm was to provide something like Hadoop, but for stream processing. Okay? So you will see that as much as MapReduce is really easy as a programming model to write code, Storm also is really easy to write for stream processing at the time. So as I said, they aspire to be the Hadoop of real-time processing when it came to light. The key properties are very similar to Hadoop. We want to be scalable. We can easily add and remove nodes from Storm cluster, fault tolerant and resilient. We need the topologies or the jobs that we will run to continue running even with failures of nodes. Extensible, it can support working with other frameworks like MySQL, for example, here. Efficient and to be used in real-time applications, and you will see that this is a bit different from Spark streaming. You will see the difference is really clear, and it guarantees no data loss. As we'll see, if the source is reliable, then even with failures of nodes, we will get all the data from that source. As I said, actually, Storm started in 2011, not even 12, by a company called Backtype, and even before 2011, and it was acquired by Twitter in 2011, and it became an open source Apache project in 2012. In 2014, more than 60 companies were using Storm, of course, besides Twitter, like Yahoo and Weather Channel. Baidu is the Chinese search engine. So it was really one of the very early and promising data streaming frameworks. So what is the data model in Storm? The job in Storm is called topology. Okay, and the reason why it is called topology, because it's actually a graph. Okay? And this graph will represent the computations that we are doing with the stream. As you know, graph contains nodes and edges. The nodes will be the processing elements or processing components. So all the transformations and operations that we want to do will be within the nodes. Edges will indicate how the nodes will communicate. Okay, so the jobs in Storm are called topologies. They are graphs. The nodes in the graph or in the topology are the processing elements. Okay, all the logic of the processing or the computations will be in the nodes. The edges will represent the communication between the nodes. Okay. Now, the main components of a topology are three things: stream, spout, and board. Okay, so we'll take each and explain what it is. Streams. This is the core abstraction in Storm, of course, and as we saw in Spark streaming, a stream is defined as an unbounded sequence, but here of tuples. Okay, so that's the general definition of a stream, and it is defined as it is in Storm. Okay, it wasn't like that in Spark streaming, right? We said that it was stream of RDDs. But here it is unbound stream, unbound sequence of tuples, records. Okay, and as you will see, it is processed and created in parallel, and the tuples are defined with a schema. There is a schema that says what are the fields in each tuple. Storm comes, of course, with the support of primitive types within the tuples, and you can also define your own custom types. Okay, so that's what we mean by stream, sequence of stream sequence of tuples. Okay, and the tuples are actually structured, so you know the schema of each tuple. Now, each stream, Storm provides in its API a way to transform that stream into another stream. Okay, and that's what we will see in Bolts, for example. Okay, so Bolts will do this transformation. So that's the main thing that you, as a user of Storm, will focus on, is to write the code that will really take a stream, either provide the stream, that will be the spout, or transform the stream into another stream, which will be the job of Bolts. So, for example, you might need to transform a stream of tweets into a stream of trending topics. Okay, so there is an input stream, but of course that stream will undergo over a set of transformations. Okay? Actually, a graph of transformations. So that's a stream. Spouts in a topology are representing the sources of streams in the topology. Okay, the source of the stream, and that can be one or more in the topology, are represented by what we call spouts. Okay, so spouts are special classes that, as you will see in Storm, that we will need to define through the API. Generally, it reads from the original source, right? If we listen to Twitter stream, then it will read from it listens to the API and provides the tweets one by one. Okay, so that's the source of the streams. Now, the spouts or the source can either be reliable or unreliable. Reliable here means that if the tuple was not processed to the end of the topology, then for some reason, maybe some nodes failed, okay, or some operations failed, then we can replay that tuple from the original source. Okay, that's what we mean by reliable. Unreliable means that once the source emitted the tuple in the stream, then it's gone. You cannot replay it. Okay, so there are two types of spouts here, and they depend, of course, on the original source. Okay, did you understand this point? Yes, it depends on the source. The source itself might not be reliable. So you have to understand that if it's not reliable, then you might lose some data. If it's reliable, then it is guaranteed that you will process every tuple from that stream, okay, from that source. Okay. For example, Twitter API. if you lost one tweet, can you ask to get it again? It's gone, خلاص, right? It will be delayed in time, and you get a copy, but it will not be in the stream anyway. But you might queue it. We might use a system of a queue that it will queue these tweets and make it reliable, make that source reliable. So it will not remove it from the queue or get rid of it until it is acknowledged that the processing is done. Okay, so these are the two types. Okay, so that's spouts. And spouts can emit more than one stream. And as you see here in the figure, this spout emits two streams. Okay, so it can actually branch to multiple, what we will call very soon boards, okay, the processing nodes in the topology. Now, boards, which is the third component, are the processing power of a storm topology. Okay, this is where the processing or the transformations will be done to the streams. So it can be linked to one board or spout or more. Depends on the application that you are doing, of course. Okay, and it will process any number of input streams, and it will process the tuples from these streams one by one. Okay, so this is different from, I think you start to see differences here from Spark streaming. There is no notion of data sets here, RDDs, right, or micro batch. It is each tuple is processed in real time. Okay, so there is no buffering here. There is no batching. Not buffering, batching. The batch, you can think of it here as the batch of one tuple, okay, which means it is real time. It's not near real time like what we had in Spark streaming. And of course, the board can do anything. It depends on what you want to do with the stream. So it can do filtering, aggregations, joins, talking to databases, okay, whatever you like to do with the stream. And boards, as I said, can be connected to spouts and or other boards. As you see here in the topology, this board is connected to two boards, which means that the stream that is coming out of this board and the stream that is coming out of this board, both are input to that board. Okay, so that board will actually process both of these streams. Or it can be connected directly to the spout. It's up to you, depending on what you need to do in your application. Usually boards, or that's the recommendation, is that boards should do simple transformations. So processing that will not take a lot of time. What if we really need to do complex transformations? Then we'll have to decompose it into multiple boards. Okay. Remember that this is a stream, so you have to be really fast. You should not block at any point. Okay. So if there is a complex transformation that you need to do, then you will have to do it using multiple boards. Yes. 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 Okay. You will see very soon that each board has multiple tasks. So the data, the stream that is coming to every board is actually distributed over multiple tasks in parallel. Okay, but these tasks are same board, like the mapper in MapReduce, or the partition RDD in Spark. It's partitioned and it's processed in parallel. Okay. Any questions so far? Right. This is a summary of the three components. So we have streams. Streams are the basic abstraction, bounded sequence of tuples. These streams are transformed by the processing elements. What are the processing elements? Boards. Okay. The boards are the processing elements. So the streams will be transformed by the processing elements into other streams. Okay. So every link in the topology is actually a stream. Okay. Every link here is a stream. The spouts, it's the generators of the stream, and it might actually stream to multiple boards, okay, multiple consumers. Boards subscribe to streams, and transform streams, and produce new ones. Okay. In a topology, as you see here, you can have multiple spouts. Of course, at least you have to have one, right? Otherwise, there's no stream. But you can have multiple, as you will see here. And of course, you have at least one board. Otherwise, you are not doing anything with the stream. Okay, but generally, you can create your own topology through, of course, the API of Store. Okay. So you will see that this relations.
How you come from the first one to the second one. Is that a transformation or?
Yes, now each board is doing, we will see examples, of course, okay, or at least one complete example. But each board is doing one processing. You can do anything with the stream, okay? But remember, as you will see, the function that we will actually implement for in a board is taking one tuple. It's like in the map function in MapReduce, right? It takes one input, one input pair, right? Here it's just one tuple, and you process it because that's a stream, right? And it will be called for each tuple. So each board will have its own logic. So it should, for example, this board takes the stream from that spout, does something, and produce another stream that will be consumed by this board. Okay, so I think we had, yeah. So let's think about this example for it.
Is it like
okay, so I know that you will start to think about this. Type. Let's go through this example together, okay, and then I will answer your question. Let's say that we have a stream of tweets, and I want to transform it into a stream of trending images. What do you mean by trending images? Images that are frequent. Okay, so what do we do? What do we need here? So first, we need a spout that will listen to Twitter API, right? Okay, so we have a spout. The spout will emit one tweet at a time. Then we need to process this tweet, right? So in streaming, think of processing one tuple, one record at a time. Okay, and that will repeat for everyone. Same like in MapReduce, right? Think of processing one input, one key value pair. Now, given one tweet, what should we do? Extract the image. Okay, then so that's the next stream. So we had the tweet stream. Now we have an image stream. Okay, then that's not yet the trending image stream, right? It's not yet the trending images. Here it's you are on your own. Okay, you do it. Yeah, let's assume. Give some assumptions. Tell me how you do it. Yes, no. We are thinking together, right? So we will get the now we have a stream of images. How would you have to save it? Okay, you are thinking sequential now. Okay. How do we do it? What do we need, طيب? يعني even if this in the sequential idea, how you do it? How do we do it? How do we get the training images? Okay. How do you know which one appears the most? Frequency. So you have to count, right? Okay. So one board will emit the image stream, and then another will count. Okay, by grouping. Okay. Okay. So the other will start to count the frequency, the number of occurrences of images. Okay, and of course we need probably you need to update that every maybe 5 or 10 minutes. Okay, so that's sequence of boards. Now, and the idea here was that this is complex to be done in one board. Of course, you cannot actually do it in one board. You can, but you shouldn't. Okay, because that's really complex transformation. So you have to decompose it into a pipeline of boards. So back to your question, how is that different, or is it similar to what we saw in Spark streaming in terms of RDDs? How is different? Okay, we didn't talk about that yet, but we said that each board here actually is multiple tasks. Yani think of the board is the logical processing unit, but it is done in parallel over the stream. Yani this, we'll see it very soon, but we said that each link here is a stream, right? Okay, so let's think about this specific link. Okay, Storm through its API allows the user to indicate how many indicate the parallelism of that board. Okay, so if I said 4, that means that this would be 4 tasks. Okay, 4 tasks can run on 4 different machines, for example. Now that stream will be distributed over 4 tasks in parallel. Okay, or 10 tasks if I define it to be 10, and so on. Okay, طيب. There's no RDDs here. Okay, we are processing one record at a time in real time. Okay, so there is no batches, there is no tables. Unless you want to count, you have to create your own data structure if you want to do something like that. Okay, but the processing is done per tuple. Okay, things will be more clear when we get to talk about actually these links, okay, and the meaning of these links. Any other questions? Okay, now let's do word count. As we did in MapReduce, that was the first one. Right. If we want to do word count, what do we need to do? Let's say that we are getting a stream of documents or tweets. Yes, read the tweets, right? Okay, so we'll have to have. So let's do it together. We have. Okay, so we'll have spout here. Okay, that will listen to Twitter. Okay, now the stream from the spout will go to board. Okay, let's say this is the board. Okay, what will that board do? Emit words. Okay, so emit words. So now this is another stream, which is words stream. Okay, so we have words here. Then, okay, you're thinking, okay, so the next one will be another board, right? We cannot get input into a spout, by the way. Spout is always the source. So we have another board here. What will that board do? Sorry. What will it do? Count. Okay. So for each word, it will have to maintain. So that will be count. Okay. And that maybe will write it somewhere. Okay. So we don't need to do any further processing here, right? There are of course some details we still didn't mention, but that will be the structure. We need to emit words and then we count them. Okay, right. Let's see how we will actually do it in store. Okay, so this is the tweet spout. Then we'll parse the tweet and generate the words, and then we count. So this one will listen to Twitter API, this one will emit the words, and this one will aggregate the counts and output the counts every 5 minutes. Okay, so that's the logic that we did, right? Right. What is missing here? Huh? So is this board very clear what to do? This one. This type, the spout, is the spout clear? It will listen to the Twitter API and emit each tweet, right? So this is straightforward. How about this one? Why it's not clear? It will get the tweet. So this is tweet. These are tweets, right? And it will generate words. So is that clear or not? It's clear, right? Just splitting the words within the tweet and emitting the words with counts of 1. There's no window here. Okay. How can we what? We didn't get to this one yet. Okay, we are still within this one. Is there any problem with this one? Type. Is this stateful or stateless? Huh? This one. Is this stateful or stateless? Stateless, right? It doesn't depend on any previous state. Just get the tweets and process it, right? Type. So this is stateless. Okay. Type. How about this one? This is stateful. Okay, this is stateful. Type. What do we need to make this one actually produce what we want? It has to save the state. What is the state? The current counts of each one. Okay. Type. How can I guarantee that I will have correct counts for all the words? What do we need? Remember in MapReduce, what did we need here to make sure that we have correct output, correct counts? Okay, we need to save the state, but to save the state, this is different from having correct output. Okay, and if I want the correct number of occurrences or frequency of the word Qatar, for example, okay, what do we need to what do we need to guarantee here? Did we say how? We mentioned that each board has multiple tasks, right? So you can think of this as actually multiple boards running, or multiple components running in parallel, right? Right? And this one is also the same. Okay? Huh? Okay. We need to make sure that each task here will get the same words. Otherwise, the word qata sometimes will go to this task, and another time will go to this task, and so on, right? Right? So what is missing here is how the stream actually is distributed between these two boards. Or in general, each link here, how that the stream is partitioned, is distributed. Okay? So this is what is missing. To which board exactly? So here we represent the tasks here by nodes inside the board or the spout. Okay? So here we have 3 tasks, here we have 3 tasks, here we have 5 tasks, and so on. So for each link in the topology, we need to know how the data will go from each task here to each task here. Okay? So when a spout or board emits a tuple, where should it go? So that's what's missing. In the previous example, do we care about this question here? We don't care, right? We don't care at all. Any tweet can go to any task, right? Doesn't matter. How about here? Here we care. Okay. So in Storm we have what we call stream groupings. Stream groupings. Stream groupings means that these are different types that will define how the stream will be partitioned among the tasks of the board. Okay, so we will discuss now 8 built-in stream groupings in Store, and still you can also have your custom grouping, but there are 8 that are built in. Okay, first I want to make sure that you understand what we mean here by groupings. Groupings here means that we need to know how the tuples from one spout or one board will be partitioned to the next board, which means that how the data is transferred between 2 components in each link in the topology. Because remember that these are running in parallel. Okay, so this is not just one task and here one task. If it's that case, then that will be sequential, right? We don't need to partition anything. Right? But here we have multiple tasks, here we have multiple tasks, and these are, by the way, user defined, and you can actually say how many tasks you want for each board or spout. So we'll have to define clearly how the data will be distributed or partitioned in each link. Is that clear? Any question about this? Because this is very important. Okay, fine. What are the 8 different built-in groupings? The first one is called shuffle grouping, which means that the data will be distributed randomly. Okay? Randomly, the data will be distributed among the tasks. Type. Will that benefit us in our example? No? In our examples, how many streams we have? We have one between the spout and the first board, and another between the second and third, right? For the first one, now grouping is for each link, right? For each edge in the topology, we have groupings. We have a type of grouping. Shuffle grouping, will that benefit us in each of these? The first one, right? The first one, between the spout and the ball, we don't care, so random is fine. Okay, so that's the first one. The second one is called fields grouping, and this is partitioned by specific field. So for example, if the stream is grouped by the user ID, so this is like grouping by the field user ID, then the tuples with the same user ID will always go to the same task. So this is like group by, right? Group by the specified field. But all the tuples of the same field will go to the same task. With the same, value of the field, of course. Okay? Tuples with different user IDs may go to different tasks. Doesn't matter. Might go to the same task, but generally it might go to different. But for the same value of the field, all the tuples that have this value will go to the same task. Okay, is this one clear? Type. Will that benefit us? What will be the field in this case? The word, right? The word. If I specified the field to be the word here, then all the tuples, all the counts for that word will always go to the same task. And that's exactly what we need to do in our example. Okay? So the first link, we should specify shuffle grouping because we don't care which will go to which. And the second should be fields grouping because we need to all the fields grouping using the word field because we need all the counts for each word to go to the same task. Okay, any question on this? Right. The third one is partial key grouping. This is like fields grouping, but it is load balanced. And Storm tries to balance the load between the different tasks. But still, all the tuples of the same value of the specified field will go to the same task. Okay. So if we need to maintain load balancing, then we should use partial key grouping. The fourth one, all grouping, and this one you should use by care. Okay? And you should really be careful when you use it, because in this case the stream will be replicated across all tasks. So all tasks will get all tuples. There might be an application that needs that. Huh? You still remember PMI? Okay, because you did it that way, right? Okay. I started to grade it and then I stopped when I saw what Aman did. It was blocked. Type. So that was an application of outgoing. Anyway, so you should be careful when you do that because that's replicating the data. Okay? And you should not do that in big data unless you really need it. Okay, the fifth one is called global grouping. In that case, you will only direct the entire stream to one task, one specific task. You will say why, right? There might be a very good. Okay, very good. I expected this question. I like this kind of questions. Why do we need multiple tasks then if we, in this case, we will say that everything will go to the same task? Just redundant يعني. Did you remember that earlier I said that one board might get multiple streams, right? Right. Will that solve the problem or not? One stream might be by global grouping, another might be random, might be something else. So the tasks still are doing something, okay? But for a specific stream, it will go to the specific task. Why? That depends on the application. Okay? But still, it's meaningful in case that this board actually listens to multiple streams. No. Okay, that's okay. Good that you, you mentioned that. If we have a board like this and it has two streams, okay? Each stream has its own grouping. We don't have to say that all the streams that are going to the board will have the same grouping. The grouping is defined per link, per stream. Okay, so that stream might be global, that stream might be shuffle, which is the random one. Okay, they don't have to be all global. You can, of course, and give each to each. That depends on the application. You can invent your own way. Okay, the API gives you this flexibility. Okay, clear? These are available types that you need to keep in mind. Maybe you will need it. Didn't you? I think I gave you this example. This was that in the exercises or the homework? I don't remember. The example of the winning and the right, and you had to have three reducers, and you direct each type to one of them. So sometimes you need to do something like this. Okay, the next one is non-grouping. In non-grouping, you don't care how the stream is grouped. Okay, so you leave it to the framework to Storm to. So currently, it is equivalent to shuffle grouping, which is random. So eventually, the boards that are defined with non-groupings will execute in the same thread. Okay, so it allows more efficiency to be done. So if I said none, I don't care, then Spark will try to optimize. Not Spark, Storm will try to optimize. So by running the board in the same thread as the source. Okay. Direct grouping. So in direct grouping, the producer of the tuple decides which task of the consumer will receive this tuple. Okay, so this is very general, very flexible. So this is for each tuple, you can specify which task. Okay, so that's the most general grouping that you can have. Okay? And don't ask me why we need that. There might be an application for that. Yes. It from the source, whether it is spout or board. Okay, we are talking about how the stream will go to the next board. That stream might be from a spout or another board. Okay, but in this case, if you define this link to be direct grouping, then the API, of course, provides a way to specify with every tuple which task will will that tuple go to? Okay. The last one is called local or shuffle. So here, if the target board has tasks in the same worker process, then the tuples will be shuffled to that one. Otherwise, it will be random. Okay, so this is very similar to non-grouping. You leave it to, but it explicitly says that you should prefer local first, and if there is nothing local, then you do random. Okay. So these are the 8 built-in groupings in Storm. Type. That means that we have to define the grouping for each what? For each stream, which is in the topology, each edge. Okay? We have to define that for each edge. Because we have to define how the data will flow, right? That's defining the data flow actually. Okay, now let's switch to system architecture. So how the Storm cluster looks like. Quite similar to Hadoop. We have a master node. In this case, it's called Nimbus. We have a cluster coordinator, manager called Zookeeper. And then we have the nodes themselves, or the workers. They are called here supervisors. Okay? So the master node, Nimbus, the worker nodes are supervisors. Each worker node is running worker processes. So each of these are processes, okay, in threads. Each one has its own thread. Okay, we'll talk in detail next. So 2 kinds of nodes, master and worker nodes. The master is called Nimbus. It is very similar to the job tracker in Hadoop. So it's responsible for distributing the code as the master node. Remember when we log into the cluster, we log into the master node and then submit our job. That means that our code actually is copied to the worker nodes. So similar things happen here by the Nimbus, which is the master node. Each worker runs the supervisor daemon and listen for tasks that are assigned by the master node. And the coordination is done by Zookeeper. Now, within each worker node, so now we are thinking about, looking at the worker node, which is in Storm called supervisor. The worker node runs multiple worker processes. Okay? So, mistakenly, I'm sorry that I said that each worker process is a thread. No, each worker process actually here is the Java virtual machine, which might run multiple threads. Okay, so each node has multiple worker processes. Each worker process belongs to one topology. Remember, this is a cluster that can run multiple topologies at the same time, like Hadoop cluster. It runs multiple jobs at the same time, right? Here, multiple topologies. The job in Storm is called a topology. So if I am now in one machine, one worker node, I might run multiple worker processes. Each one will belong to one topology. Okay? Type. Each worker process runs multiple executors. You can think of each executor as a thread. Okay? Usually each executor runs one task, which is the actual processing process, computing process. Okay? So the actual work of the board or spout is run by the task. But this is the hierarchy. The node has multiple processes. Each process belongs to one topology. Now, within that topology, I might have multiple executors. Each one run its own task. By default, it is one task per executor, but we might actually run also, if the user defined multiple tasks, we might run multiple tasks within the same executor. But each executor is one thread. Okay? If you didn't, and each executor runs for one board or spout. Okay? So here we are at the level of a topology. Each process belongs to one topology. Here we are at the level of the one component within the topology. Okay? So if that executor has multiple tasks, all of them belong to the same board or spout. Okay? All of these executors belong to the same topology. Okay? Because they belong to the same worker process. Okay. Here is another view. So the worker process might have, so now these boxes, the white boxes, are the executors. Okay? And the color indicates the board or spout. Okay? So worker process belongs to one topology. Within that topology, it might run one executor for that board, another executor for the same board, a third executor for another board or spout. Okay? And that one, for example, has two tasks. Okay, so you see now the structure of the cluster, and of course this is one worker process within worker node. And in the cluster, of course, we have multiple nodes. Okay? Is this clear? Now each of these tasks are the actual processing element. Okay, let me make sure that we covered all of this here. So the worker process executes a subset of a topology, belongs to a specific topology, may run one or more executors. Executor is a thread. It may run one or more tasks. I think we covered everything. Okay. Here is another example. Let's say that we have this topology. We have blue spout, green board, and yellow board. The user can specify the number of tasks through the API using what is called Parallelism Hints. Okay, so this number is the number of actually the number of executors. Okay, that's the number of executors, total number of executors that you want for this element. Okay, and also the API provides a mechanism to indicate how many tasks per executor. If you didn't, then it is by default one task per executor. So here, the parallelism hint for this one is 2, for this one is 2, for this one is 6. So the combined parallelism is 10. That means that we have to run 10 executors over the cluster for this topology. Okay? With me? Okay. Here is, we assume that we have two worker processes. So each one will take 5 executors, and this is the division or the distribution of the tasks among them. So again, this is one worker process, and this is another worker process. They might actually run on different nodes. Okay? Fine. This is in one node. It has 1, 2, 3, 4, 5 executors. And you will see that same here. And you will see that the blue spout, we said that we have 2 executors. This is one, and this is another. Okay? The green one has 2. But here for the green one, it was configured to use 2 executors and 4 tasks. That's why that each executor for the green one has 2 tasks. And overall, it has 4 tasks. for this green board. For the yellow one, it is 6 executors, 3 here and 3 there. Okay? So that's the distribution of tasks among the worker nodes. Any question about this? We'll not talk about how, of course, this is done, but that's when you specify the parallelism hint. That's the number of executors. You can also specify the number of tasks. If not, then it will be 1 task per executor. Any questions about this? Yes. Yes, we said that each executor is a thread, is running in a thread. Okay, so the number of executors is the number of threads. Any other questions? Okay, now let's talk about reliability. Storm makes sure that every tuple from spout will be fully processed by the topology. How is that? It is done by tracking the tree of tuples triggered by every spout tuple and determine if it is completely successfully completed or not. What does that mean? If I have, let's say that we have spout, okay, and we emitted one tweet, T. This tweet has 3 words or 2 words. Okay, so it will go to this board, that's out, and this board will generate two tuples, right? W1 and W2. Okay, and let's say that this is it. Halas, this is, and this will be maybe stored somewhere. So this tweet, this tuple from the source, generated 2 other tuples. Once they are fully processed, then we know that this tuple is fully processed. Okay? If one of these is failed to be generated or to be processed for some reason, then this tuple will be replayed from the spout, of course, if the spout is reliable. Okay? Right. How Storm is making sure of this? Storm tracks the tree of tuples generated by each source tuple, which means that we'll have a tree like this: T, W1, W2. And if we have another board here that will generate 2 or 3 tuples from each word, then we will have maybe x1, x2, x3 for this one, and y1, y2, y3 for this one. So this is a tree of tuples. Okay? If all of these processed, and let's say that this is the end of the topology, if all of these are generated fully and completed the processing, then this tuple is done. Okay? How Storm tracks this? It actually tracks this tree. If this was failed at some point, so this board failed to generate this tuple, then we'll go back, then this tuple is not fully processed. So we'll go back and get that tuple, replay it from the source spout. Does that remind you of something similar? the lineage. Okay, that's the lineage. That's actually lineage graph. But here it's at the data level. Okay, at each tuple. Okay, there it was a graph of transformations, which is, of course, there is a mapping. Okay, but that was actually before Spark streaming. And that idea of Storm was actually before Spark streaming, but it's very similar to what Spark streaming is doing. Okay, so this is how Storm maintains their reliability, which means that every tuple will be actually run at least once. There is a mechanism also within the API which is allowing this, which is called ACK or fail. So these are functions that the user can provide, and they will be called by the system whenever a tuple is fully processed. The ACK function will be called. So if you want to do any code there, you can. And if it failed, then you can provide code that will actually get it, will do something if it failed. Okay, so this is mechanism that is given to the user of Storm to act upon any failure or any success of each tuple. Okay, any questions so far? What remains is that we'll go through an example implemented in code. Okay, I forgot to tell you that Storm actually provides supports any programming language. You can use your own. Okay, but the examples that we will show here are in Java. Any questions? So did you get the idea of Storm now? Any questions? Ali? Okay. This example assumes that we have an input of, so this is of course a toy example, just to show you some snippets of code. The input here is something like a log file of commits. Okay, so we have repository of code, and there are multiple contributors to this repository, and we eventually want to see for each contributor how many commits he or she did. Okay, so this is like counting also. Okay, so we need to count the commits for each contributor. Type. The topology is, I think, straightforward. We start with the stream of commits. Okay, the stream of commits here are defined as follows. Each tuple has a commit ID and the ID of the user. Okay, now from that, we don't care about the ID, right? We need the user. So we will read, so this is the spout, the first spout. It will read commits from the feed and provide this. So this is the first spout. We'll provide each tuple. And then we will need to extract the email. Then we need to count. Okay, so this is very similar to the example that we started with, the word count example. Right. Let's see the code here. Of course, we will not go through every line, but we'll give you a quick overview of what is that. First, there are. Let's think together what we need to define here. Can you tell me what you think we need to define? I know that you don't know the API, right? But what are the things that, as a programmer, you need to define here? There must be, of course, you will write code for each component here, right? So for the spout, you will provide the code for the spout. You will provide another for each of these boards, right? Okay, so there must be, you will have to write code for each of these components. Type. How about the topology itself? You need to define the topology, right? You need to define that this board, so this is, let's say this is board number 1, and this is board number 2. You need to specify that there is a link between this spout and that board, right? Or in other words, this board listens to the stream of that spout, and that this board listens to the stream of that board. Okay, so that defines the topology, right? So we must define the topology somehow. What else? What is remaining here? So this is exactly the word count example, right? So we said that also we need to define the grouping for each link. Okay, so we need to define the grouping for each link. So this is basically, I think, everything that, at least for this example, we need to define. So I start with the topology. So you define the topology builder, and then you start to set the components. Okay. Of course, you need to write these components to assume that they are written. So we have the this is the first. This is the code for the class for the object for the spout. Okay. So we set the spout. This is the code for the spout, and this is the like the name of the spout. Okay. Then we set the first board. So this is the code for the first board. So this is the spout. This is board 1. And that's the name for that board. Now, this is dot shuffle, so focus with me on this. Shuffle grouping, commit, feed, listener. What is this? What is commit, feed, listener? This is this one, right? That's the spout. So this is defining the link between the link that is coming from the spout into board 1, and at the same time defining the grouping. Remember, the grouping for the first link in the word count example was random, right? So that's why we have a shuffle grouping here. Okay, following with me, everyone? Reem, are you with us? Okay. Now, how about the second board? So for the second board, I want you to focus with me. For the second board, we need to define the link. Okay, so assume that the class is there, the object is there for the second board, and then we define the link. How do we define the link? Which grouping we should use? Fields grouping, and in that case we need to specify the field. Okay, we need to specify the field. So you will see here that set board here, it gives a name to the third board, to the second board, board 2. So this is board 2. And then use fields grouping with board 1. So email extractor is board 1, is the name of board 1. Okay? And it has to specify the fields. So here the fields is email. Type. Where is email here? Email, you will not find it in this code. Email is a field within the stream that is emitted by board 1. board 1. So you will remember that in email extractor you will see that we will define the names of the fields. Okay, you will see email there. And that's it. That's the topology. So we will create the topology, and this will submit it. Okay, so that's defining the topology. Now let's look quickly at the spout and the two boards. So you will see here output collector, which is the object that you will use to emit tuples. Does it remind you of something? output collector? You haven't heard about something like this? No. Further in time. Did you start your semester by Spark? By MapReduce, right? Or Hadoop? Do you remember something like this? Output collector? Okay, what is in the new versions? Huh? There is an object that you use to emit the context. Exactly. Yes. Okay. But same job here. It is used to emit tuples here. Okay. Here, because this is just a toy example, the commits stream comes from a list. Okay, but of course, in reality, it doesn't come from static list. So that's the continuation of the spout code. You will see here that we declare, there is a function called declare output fields. This is the schema of the stream, the output stream. Okay, so in the for the spout, it is just one field which is called commit. Open is like the initialization or the setup function in MapReduce. Okay, it's called once in the beginning, just to prepare the stream, and then next tuple is called to emit the actual tuples. Okay, so this is a bit specific to the toy example, so we'll not focus on that. Email extractor is the first board. If you remember, I told you that we will find the email field there. So here it is. The commit, if you remember, the commit has the ID and the email. So we'll have to split it and emit only the second part, which is the email. So in this board we override the declare output field, which declares the schema. We only have one field here. Execute is the function that will be called for each incoming tuple. Okay, so each new tuple will be fed to this function, and this function will emit whatever it needs. Are you following with me? Okay, now this is port 1. This is port 1. It emits emails. Okay, now if you remember, between port 1 and port 2 there was the fields grouping. So each email, the tuples that have the same email will go to the same task. Okay, so we can actually count them. So now we'll see the code for the email counter. So the email counter, what is the output of it? Nothing. It doesn't do any output. Just a toy example doesn't give any output. Just keep continuing, keep counting. Okay, so there's no schema for the output. So you'll see that this function actually is empty. Okay, now how will we count? We need the data structure, right? We need something like the hash map or tree map to actually count the number of times you see each email. So you define it, you create it in the prepare function. Prepare function is something like the setup function that is called once. And then execute is called with each tuple. So whenever we get a new email, so that's the new email, that's the email from the tuple, we add it to the hash map, typically, as we do typically. Okay? And here in that code we print the counts every time. And this is just helper functions. Now, yes. Yeah. That's this code runs locally, so that's just a debugging code. But of course, you should not do that in production or on large scale. What I wanted to say here is that this code runs where? We remember the architecture of the system, of the cluster. We have worker node. Worker node has worker process. Worker process has executors, and within the executors there are tasks. So where is that code runs, actually? In a task, okay? In a task, okay? And it is in all tasks in parallel. So let's say that we have 3 tasks, okay? So that now these 3 tasks are running that code in parallel, waiting for the tuples to come in, okay? So we have 3 tasks in parallel here. And let's say that we have 4 tasks from the previous bolt. So this is bolt 1, this is bolt 2, okay? And what was the type of the grouping? Fields. So you expect that there is something like this, right? Depending on the values of the emails. Now let's look at this task. Okay. So this task will get all the let's say that I was one of the contributors, so all of my email, all tuples that have my email will go to this task, and all tuples that have a man's email will go to the same task, okay? But Fatma and Ali will go to that task, and Reem will go to the third task, okay? So each task here has its own hash map, has its own statistics or counts, or it is just one. I was saying the whole story for this question. Is it one hash map or multiple hash maps? Multiple. One at each task? One at each task? Why not? We said that this code runs at the task level, right? So that means that this one is here. There's another one, completely different, completely independent, here, and the third one here. You would like to map always to your golden age, to map reduce. Yes, but it doesn't have to be reducers always. It depends on the type of the grouping. Okay? Yeah, so these are like different, they are different tasks. Don't call them reducers. Okay? Different tasks running in parallel. So did you get it, Fatma? Okay, so, but to maintain correctness, you have to define this as fields grouping. Otherwise, we would not have actually correct counts at the end. Okay? Is that clear, Fatma? Any questions about this? Okay, so what remains is a quick comparison between Storm and Spark streaming. So in terms of processing model, we have batch processing, stream processing, and micro batching, and this is what we covered in class, right? Batch processing. In batch processing, we process the data en masse at once. The batch size could be small or very large, and of course, batch processing frameworks excels when we have really large amount of stable existing data. That's why it's called batch. On the other hand, and that's of course includes high latency because we will process this huge data, okay, in sequence. And this is not suitable for data streams, right? For stream processing, one at a time processing model, each datum means one tuple, is processed as it arrives. Which of the frameworks that we covered belongs to this type? Storm or sparse streaming? One at a time. Sparse streaming? So which one is this? Is it storm? Storm, right? We process one tuple at a time as it arrives. So this is one at a time processing. And that's the actual stream processing. Yani the original meaning of stream processing is to process each one at each tuple or item or datum as it arrives. And of course, it excels at computing transformations or processing the data as they are injected with very small latencies. But it is inefficient to process stable data and batches of data, okay? Because it actually processes one at a time, then it's not efficient to process very large stable data. Stable means here existing data. Okay? And there's a third type, which is micro-batching. And it is a special case of batch processing where the batch size is very, very small. Which one is here? Spark streaming. Okay? So this is the mix between batching and streaming. It has some, of course, cost of latency because we have to create these batches, mini batches. But it is at the middle of the stream between the one at a time processing and batch processing. Where are we? This is the batch area, and this is the streaming area. Micro batch is here, right? Because it's a mix between these two. It is batch by nature because we are working with batches, but they are very small, so it is very close to streaming. Spark is here, Storm is here, and Spark streaming is here. And there is a version of Storm that is doing micro batching. We'll not cover in class. It is called Trident. Okay, so this is similar to Spark streaming, but it is the micro batch version of Storm. Okay. So Storm is a stream processing framework that also does micro batching, and Spark is a batch processing framework that also does micro batching. Okay, I want you to remember this and then understand it. Okay, so Storm originally is a streaming framework, but there is a version of it that's micro batching. Spark is originally batch processing framework, and there is a version of it that is micro batching, which is Spark streaming. This is summarizing the comparison between Storm and Spark streaming. Storm process record at a time. This is mini batching here. The latency of Storm, of course, is better because it processes every tuple as it arrives. The delivery here at least once because we might need to replay the tuples if they fail. Here it is exactly once. Stateful operations. Of course, we saw stateful operations in Spark streaming. No here doesn't mean that you cannot do it, but you have to do it on your own. Here it is supported, okay? And there are many built-in functions that you can use. Here, if you want to do window, you have to do it yourself. There is no support for window, at least at the version that I looked at. But Spark streaming has it. In terms of development code, if you are working also with batch processing, of course, that will be separate because it is not batch processing. But with Spark streaming, Spark is there, very similar in code, so it will be easier to integrate. The community that is using Storm is much less than Spark. Twitter is behind it, but here it is much larger. But is that the right comparison? Yani, are we here comparing apples with apples? No. So what is the right comparison? I mean, if we want to compare with, sorry, if we want to compare with something with spark streaming, what should we compare? Trident, exactly. Okay, Trident, because that's the version that is micro-batching. That should be more suitable to compare with spark streaming.